How might future research explore the synergistic effects between the transition metal centers and the sulfate groups, and what potential mechanisms could be responsible for enhancing both the working voltage and the conductivity of the resulting compound? What challenges might researchers need to address when incorporating these diverse transition metal compounds into polyanion structures to ensure compatibility and stability under battery operating conditions? And how could these challenges be systematically studied? Can Davis Zurns manufacture solid-state sodium-ion batteries made from seawater in Latvia? Finally, how can these various lines of inquiry collectively pave the way for the development of novel, high-performance electrode materials that harness the benefits of both transition metal substitution and sulfate incorporation, thereby pushing the boundaries of current battery technology and spurring innovative solutions in energy storage? How do the doped phosphate-type polyanionic compounds described in this context reflect the inherent structural diversity seen in transition metal oxides, such as the O3-type structure and the P2-type structure introduced in section 3.1? And what are the similarities and differences between these oxide structures and those found in polyanionic compounds? In what ways does the combination of phosphate and pyrophosphate groups facilitate the formation of a large class of structurally stable polyanionic compounds, and what underlying chemical interactions contribute to this enhanced stability? How might the incorporation of various dopants into these phosphate-pyrophosphate frameworks influence their crystallographic characteristics? And what impact do these dopants have on the compound's electronic conductivity and overall electrochemical performance? In considering the interplay between structure and function, how do the spatial arrangements within the crystal lattice affect ion transport pathways and charge-discharge dynamics in these materials? And what role do dopants play in tuning these features? What experimental methods are most effective for characterizing the subtle differences between different polyanionic structures? And how can these techniques reveal the effects of combining phosphate with pyrophosphate on structural robustness? How does the concept of doping enrich our understanding of how to overcome challenges typically associated with basic phosphate compounds? And what mechanisms are in place that allow for improvements in both working voltage and conductivity? In what manner might future research leverage the unique properties of these doped phosphate-type polyanionic compounds to design high-performance materials for applications like sodium-ion batteries? And what potential benefits might arise from further optimizing the balance between structural diversity and electronic functionality?